factoring weird things. Okay, let's start off with something that you guys probably can all factor. This is a quadratic, but it's not a trinomial. 8x squared plus 4x. This is a weird thing, according to my very technical terminology, because it does not follow the form ax squared plus bx plus c. Well, actually it does. It's just that c is 0 here. So this is kind of the least weird of the things that we're going to look at. What do you do to factor this? Well, it's actually even easier than what we've been practicing. If I just have two terms, I simply factor out my greatest common factor. So here I notice an 8x squared plus 4x. Those both have a 4, and they both have an x. So I factor this as 4x times 8x squared divided by 4x is 2x plus 4x divided by 4x is 1. Usually we write them like this. You can write it like this if you want to. That's totally fine. But you don't need these parentheses because there's only one term in the first factor. Okay. If I asked you to find the zeros here, it's the same thing that we've been doing. I set this factor equal to 0. And then I set this factor equal to 0. The cool thing about these is that as long as you have an x in both terms, one of your factors, one of your zeros will always be 0. Right? One of your factors will equal 0, and then you get 0 as the x. The other one is just like when we have two factors of two terms, right? Two binomials. Subtract 1, 2x equals negative 1, divide by 2, so x equals negative 1/2. So that would be my zeros. These would be my factors if I don't have a c term. Sometimes what happens is you look at these and you kind of stare at them and go, wait a second, I need factors of this that add up to this. How am I going to do that? But it's actually the step before that, right? It's, can you factor out a greatest common factor? Okay, so this is sort of a silly example of a weird thing. The other things we're going to look at are much weirder. All right. Let's say you had this. This is going to be weird for a couple different reasons. N to the 6th power plus 5n to the 5th power plus 6. So you look at this and you go, whoa, wait a second. We're only on quadratics. We have a long way to go before I can do n to the 6th, right? Or x to the 6th. One thing I want to point out, the variable doesn't matter, right? We usually use x. Hold on a second. We usually use x, but we can have n or p or t or v or w or some weird Greek letter like alpha. The variable really will not matter for our purposes. So don't let that throw you off. The other thing is we can actually factor this the same way we did the last one. All we have to do is get our greatest common factor out. In this case, our greatest common factor is n to the 4th. So if I pull an n to the 4th out, all of a sudden, n squared plus 5n plus 6, this looks a lot more familiar. when I factor this, I have to remember that the n to the 4 is still there. And that's, I think, the trickiest part, actually. When you get to the last step, don't forget about this. So in this example, I'm looking for factors of 6 that add up to 5. Basically, I'm just focusing on this now. And I'm kind of ignoring everything else. So factors of 6 that add up to 5. Okay, how about 2 and 3? Aha, that works. But if I just circle this, I'm almost there. I forgot my n to the 4th. So our final answer is n to the 4th times n plus 2 times n plus 3. We just have kind of this weird extra thing hanging off the front. And just like in the last one, it's only one term, so we can put the parentheses, but we certainly don't have to put the parentheses. Okay. Can I erase? Not quite. Let me get the next problem. Ready? Okay. Last thing that will be on your homework for this is this type of problem. Let's say I had x squared plus 17xy plus 16y squared. So this looks weird because you're like, wait a second. 2 variables? How am I going to factor 2 variables? The cool thing is, as long as they follow this pattern, it doesn't, you can kind of ignore the variable. Think about it. If I gave you this to factor, and you described the procedure to me, I'm going to think of factors of 16 that add up to 17. Do you ever say anything about x? Not really, right? We kind of ignore it. As long as it follows the pattern x squared x, this is actually x to the 0, right? We don't really think about x when we factor. As long as your second variable follows the pattern of y squared, y, and then y to the 0, or nothing, right? You can kind of ignore the y. What happens is my second term in both of my factors will have a y attached to it. So watch this. I know that the basic pattern for something like this is something x plus something y times something x plus something y. So all I'm looking for is what are the somethings? What do I put in front of the x? Well, in this case, it's x squared. There's nothing in front of x squared. So I know that it's just x. In other words, there's a 1 in front of x that we don't write, an invisible 1. So in this problem, I'm only looking for what goes in front of y. And it's the same thing that we've been doing. I need factors of 16 that add up to 17. So in this case, 16 and 1. And if you don't believe that, FOIL it. So let's FOIL this. I'm going to take my first term times my first term. That's x times x, or x squared. My outside term times the other outside. That's x times 1y, which is xy, or 1xy. Inside, 16y times x. And then last, 16y times 1y, which is 16y squared. Wait a second. I must have done something wrong. This isn't the same as this. Or is it? Yeah. I don't have any like terms. I have x squared, xy, yx, and y squared. What like terms are you talking about? Yeah.
X, y, and y are the same.
Yeah, this is the same as this. Right? Commutative property of multiplication. I can just write x squared plus xy plus 16xy plus 16y squared. Now I see the like terms. X squared plus 17xy plus 16y squared. Phew. Second thought, I thought I had made a mistake. Okay. So that's our answer. The key is just to kind of notice the pattern of like descending y's from the right. Y squared, y, nothing. And then think, okay, I know I'm going to have an x and a y. What are the coefficients? That's all you're really looking for. Let's do another one like that. Let's say you had 5x squared 7xy. This is a little harder because now we have something in front of x, right? Can I erase? Okay. The key here is we realize x squared x, no x, y squared y, no y. I'm just going to forget about the x's and y's. I'm only going to pay attention to the coefficients. Okay? So I use Gary's terrific trick. What are factors of 5 times negative 6 that add up to 7? How about 10 and negative 3? Okay. Let's try that. I'm going to rewrite my middle term. So 5x squared minus 3xy plus 10xy minus 6y squared.
Well, wouldn't it just be easier to do 5 and 10 together instead of 5 and negative 3? And negative 3 and negative 6 instead of 10?
Yeah, you could. Totally. I'm going to do it this way because I like keeping the negative here. But you could totally write the 10 first and then the negative 3 second. All right. In the first group, I have x as the only thing in common. So I pull out x. I have 5x minus 3y left. Plus, in my second group, I have 2y in common. So I have 5x minus 3y left over. I pull out my blob, which is 5x minus 3y. And left, I have an x plus a 2y. I would recommend if you're doing a quiz or test that you FOIL this to check. We'll just do it out loud. 5x times x is 5x squared. 5x times 2y is 10xy minus 3xy. That gives me the 7xy. And then negative 3y times positive 2y is negative 6y squared. So that works if we FOIL it. All right, I want to show you one other thing. This is not on the homework tonight, but it's just kind of a cool trick. Let's say I had something like this. X to the 4th plus 3x squared plus 2. Can I erase this? So again, we've only learned to factor things that have squares, right? Well, now you've learned that if you can pull out a greatest common factor, you might be able to factor something bigger. But here there's nothing that I can pull out, right? Because there's no x here. So instead, there's a couple ways to think about this. Here's how I think about it. I know that I have an x in the first term and an x in the second term. So this is kind of acting like the trinomials that we know. It has an x, it doesn't have an x. So what I'm going to try to do is I'm going to say, let's create another variable. We'll call it y, and y will be equal to whatever this is. So in this case, I'm going to say y is equal to x squared. Let's see what y squared is. Y squared is x squared squared, which is x to the 4th. If this is this, right, minus the coefficient. It's okay if you have a coefficient here, but if the degree on this variable is equal to the degree on this one, then we can use sort of a substitution method to factor this, which I think is really cool. So watch what I'm going to do. I'm going to write y squared instead of x to the 4th, because those are equal. I'm going to write y instead of x squared. And now I have a quadratic that I can factor. Hopefully, if I wrote it correctly. Okay. Y plus 2 times y plus 1, because 2 and 1 are factors of 2 that add up to 3. And then there's just one final step. They gave me a problem with x's, so they're going to be pretty confused if I give them y's back. I need to plug the x back in, and I know that y is equal to x squared. So the factors here are x squared plus 2 times x squared plus 1. The really cool thing about this is it will work with all sorts of weird looking stuff, right? Using this trick, you can sometimes factor stuff that has square roots, or that has like x to the 200. As long as it follows this pattern right here, right? So remember, we set it up by saying, if y equals this, what is y squared? And if it's this, then you can factor it. Okay. All right, I'm going to turn this off.